somewhere beneath your feet. Right now, the ground you think of as solid, permanent, unmoving is doing something scientists did not expect. It is cooling faster than it should. It is recycling itself faster than it should. In some places, it is rising out of the ocean faster than it should. And in a handful of research papers published only in the last few years, a quiet but unsettling picture has started to come together. The planet we live on is not the slow, sleepy rock we were taught about in school. It is a restless, churning, accelerating machine, and we have only just begun to understand why. If you subscribe to this channel, you already know we don't do surface-level science here. We go underneath, literally in this case, because the story of Earth's crust is not really a story about rocks. It's a story about time itself, about how something that was supposed to take 2 billion years to happen is now measured in 500 million. It's a story about a chunk of Africa that refuses to break apart when everything around it is tearing open. And it's a story about ice, of all things, revealing that the layer of the Earth beneath the crust is far more fluid, it's far more responsive than any geologist expected even 15 years ago. By the end of this, you're going to look at a map of the world differently. You're going to understand why continents assemble into supercontinents and then violently break apart on a rhythm we can now actually measure. And you're going to be left with a question that the world's leading geophysicists are still arguing about. If the Earth is changing this much faster than we thought, what does that tell us about the planets we haven't even reached yet? For most of human history, the ground was the one thing nobody questioned. Ancient civilizations built entire cosmologies on the assumption that the Earth beneath them was fixed, eternal, the unmoving stage on which the sky performed its slow rotations. Sailors mapped coastlines as permanent boundaries. Farmers assumed the mountains. Ringing their valleys had always looked exactly as they did in that moment, and always would. Even early geologists, once they finally accepted that the Earth was ancient, hundreds of millions of years old rather than a few thousand, still imagined its interior as something close to finished, a planet that had done most of its violent evolving long ago and had since settled into a slow, dignified old age. It took the theory of plate tectonics, not fully accepted by the scientific mainstream until the 1960s, to shatter that illusion and reveal a planet whose surface is in constant, restless motion. And now, just a few decades after that revolution, an even deeper one is unfolding, showing that even the tectonic model we built to replace the old static picture was still too conservative, too slow, to capture what is actually happening beneath our feet. Let's start with the basic picture, the one most of us grew up with. Earth's crust, the thin outer shell of solid rock we live on, was supposed to behave like a slow motion conveyor belt. New crust forms at mid-ocean ridges, where magma rises from the mantle below and cools into rock. That new crust then spreads outward over millions of years, eventually sinking back down into the mantle at subduction zones, where one plate dives beneath another. This cycle, this creation and destruction, was thought to take somewhere in the range of 2 billion years to complete for any given patch of oceanic crust. 2 billion years. For context, that's roughly half the entire age of the Earth. It was one of the slowest processes we could imagine. A geological heartbeat so faint it barely registered against the span of a human lifetime. Then researchers started digging into the isotopic signatures locked inside ancient rock. Samples, tracing the chemical fingerprints that record how long crust has existed before being pulled back into the planet's interior, and the numbers didn't match the old model. Instead of 2 billion years, the evidence pointed to something closer to 500 million years for the average lifespan of oceanic crust. That is a four-fold acceleration. Imagine being told that a process you thought took an entire human civilization's worth of time actually happens 4 times faster, over and over again. All across the planet, for the entire history of plate tectonics. Blanket thrown over a fire, trapping heat that would otherwise escape more efficiently through multiple smaller plates and their networks of mid-ocean ridges. Trapped heat builds, softening and weakening the crust from below, till the accumulated pressure eventually finds a way to break the insulating blanket apart. Rip the blanket open, and the newly exposed mantle vents heat far more efficiently. which is exactly the accelerated cooling signature researchers detected in crust formed after Pangaea's breakup. It's a feedback loop operating across hundreds of millions of years, heat building until it breaks its own container, then escaping until the pieces slowly gather themselves back together and the whole cycle begins again. Think about what that means. It's the very shape of the world map. The positions of the continents you can point to on a globe right now may be nothing more than a snapshot of a much larger thermal cycle the planet has been running since its formation. Over and over, an engine venting heat through the violent rearrangement of everything on its surface. And here's the part that should sit with you for a moment. If that cycle really is accelerating, if this cooling is happening twice, as fast as it used to, then the modern arrangement of continents may not last as long as the ancient supercontinents did. The clock, quite literally, is running faster than it used to. Now, if a planet-wide cooling engine sounds abstract, here's where it becomes something you can almost watch happen in real time. In the Antarctic Peninsula, researchers noticed something that shouldn't have been possible under the old understanding of how the crust responds to changes above it. As climate change accelerates the melting of the ice sheets covering parts of Antarctica, the weight pressing down on the crust beneath that ice is being lifted. Remove the weight, and the crust responds by rising, a process geologists call rebound. Under the traditional model, this rebound was expected to unfold over thousands of years. Slow, almost imperceptible readjustment as the solid rock beneath gradually resettles. But when an international team of researchers, using GPS instruments installed across the region, actually measured the rate of uplift in the northern Antarctic Peninsula, they found the ground rising at roughly 15 millimeters a year. That may not sound dramatic, but in geological terms, it is explosive. It is a rate that cannot be explained by the elastic, spring-like response of solid rock alone. Something else had to be happening. What they discovered was that the mantle beneath this specific patch of Antarctica is unusually fluid, flowing far more easily than mantle rock typically does elsewhere, likely due to subtle differences in temperature or chemical composition. Because it flows more easily, it responds to the lightning load above it almost instantly, on a time scale of years and decades rather than millennia. One of the lead researchers on that study put it about as plainly as a scientist ever does when describing something that defies expectation. You would expect this kind of rebound to unfold over thousands of years. Instead, they measured meaningful movement within just over a decade. You can, in her words, almost see it happening. For a field built on studying processes that unfold across millions or billions of years, watching the crust visibly shift within a human research career is nothing short of remarkable. It means, in at least some places on this planet, the boundary between solid rock and flowing mantle is far more responsive, far more alive than the textbooks ever suggested. And that raises an uncomfortable question for anyone thinking about the near future. If ice loss elsewhere on the planet accelerates as the climate continues to warm, are there other hidden pockets of unusually fluid mantle waiting to respond in ways we haven't measured yet? Are there parts of the crust primed to rise or sink or shift faster than anyone currently expects? The Antarctic Peninsula might not be a one-off anomaly, might be a preview. If that were the whole story, it would already be enough to rewrite a chapter of geology textbooks. But there's another thread to this, one that flips the entire narrative on its head, because not every part of the crust is speeding up. Some parts are doing the opposite. Parts are refusing to break, even when everything around them is tearing apart. Head to East Africa, to a region called the Turkana Depression, spanning northern Kenya and southern Ethiopia. This is part of the East African Rift, one of the very few places on the planet where you can watch continental breakup happening in real time, where the African continent is slowly splitting into two separate landmasses, a process that will tens of millions of years from now open an entirely new ocean basin. Rift zones like this are where scientists expect the crust to be at its weakest, thinned and stretched to the point of tearing. But researchers working with an international team, including scientists from the University of Montana, Imperial College London, and universities across Ethiopia and Kenya, found something that didn't fit the pattern. A portion of crust in this region, one that had been stretched and thinned by ancient rifting long ago, was not behaving like a weak point at all. It was behaving like a rigid, resistant block, actively pushing back against the deformation happening all around it. forcing the rift to bend around it rather than tear straight through.
Ow.
This matters because the East African Rift is not just an academic curiosity. It is quite literally a window into how new oceans are born. Geologists studying this region are essentially watching the opening chapters of a process that has played out many times across Earth's history, the slow transformation of a continental interior into a coastline, and eventually into a fully formed ocean basin. The same process that once split apart the ancient supercontinent Gondwana and opened the South Atlantic between South America and Africa. Understanding why some sections of crust resist that process while others give way tells scientists not just where the next ocean will open millions of years from now, but rewrites the underlying rules for how continental breakup works everywhere on the planet. Rules that were assumed to be well understood until this discovery came along. Why would a piece of crust that had already been thinned and stretched in the past somehow become stronger, more resistant rather than weaker over time? The answer traces back roughly 80 million years to a major heating event that struck this region long before the current rifting began. During that ancient episode, the deep layers of this section of crust lost much of their internal water and carbon dioxide, essentially drying out at a molecular level. That dehydration transformed the physical properties of the rock, leaving it denser, stiffer, dramatically more resistant to bending and cracking than the surrounding material. In other words, an event that happened tens of millions of years before humans existed. Before most of the animals we'd recognize today had even evolved, left an invisible scar deep in the crust. One that is only now revealing itself as this ancient plate tries and fails to tear this particular block apart. The implications go well beyond one patch of East Africa. This discovery suggests that where continents eventually break apart isn't governed simply by where the crust happens to be thinnest today. It's governed by the deep, invisible memory of what happened to that crust tens of millions of years earlier. Ancient chemistry, locked away far below the surface, is quietly steering the geography of tomorrow's oceans. Now put these threads side by side, because this is where the picture stops being a collection of curious facts and starts becoming something closer to a portrait of a planet in motion on multiple timescales all at once. The mantle beneath our feet is cooling twice as fast as it used to, ever since a supercontinent broke apart 170 million years ago. The crust it produces is recycling back into the interior, on a cycle 4 times shorter than scientists once believed, done and reborn in 500 million years rather than 2 billion. In specific places like Antarctica, the boundary between crust and mantle is proving to be so fluid that geological rebound, once thought to take millennia, is now measurable within a single decade. And in other places like East Africa, ancient chemical changes from tens of millions of years ago are actively resisting the very forces trying to tear the crust apart today, rerouting the future shape of continents around invisible zones of strength. None of these are separate, disconnected curiosities. They are different expressions of the same underlying truth. Earth's interior is not a static, sluggish machine ticking along at a single, predictable pace. It is a dynamic system with feedback loops, hidden variability, and thresholds we are only now learning to detect because our instruments and our sampling methods have finally become precise enough to catch it in the act. And this is where the story widens out. Because if our own planet has been hiding this much complexity in its crust for the entire span of scientific inquiry, what does that mean for how we study other worlds? Consider Venus, Earth's so-called sister planet, similar in size and composition, yet a planet that appears to lack the kind of plate tectonics we take for granted here. Researchers studying Earth's ancient crustal growth have specifically pointed to Venus as a comparison case, because understanding how Earth's crust formed and evolved gives scientists a baseline for figuring out why Venus turned out so differently. If Earth's own crustal recycling and mantle cooling rates were this far off from what models predicted, then every planetary model built using Earth as the reference point, models used to interpret the surfaces of Venus, Mars, and the rocky exoplanets we're now discovering by the thousands, may need a fundamental recalibration. That's the twist buried in the middle of this story, the one that turns a planetary science update into something much bigger. And it forces a question that most people never think to ask when they see a headline about a newly discovered exoplanet. How do scientists actually decide whether a distant rocky world could be habitable, when all they have to work with is a faint dip in starlight or a handful of atmospheric spectral lines captured from trillions of miles away? The answer is that they build models, mathematical simulations of a planet's interior, its heat budget, its crustal behavior over billions of years, and they calibrate those models using the one rocky planet we can actually study up close: Earth. Every assumption baked into those models about how quickly a young rocky planet should cool, how efficiently it should recycle its crust, how long it should remain geologically active enough to sustain a magnetic field and a stable climate, traces back to what we thought we understood about our own world's internal clock. We often talk about exoplanet discoveries as the frontier of understanding whether other worlds could host life. Space telescopes scan the atmospheres of rocky planets orbiting distant stars, searching for the chemical signatures of habitability. But nearly all of those models depend on assumptions about how quickly a rocky planet's interior cools, how its crust forms and recycles, how efficiently it can regulate its internal temperature over billions of years, because that regulation is tied directly to whether a planet can sustain the kind of stable, long-term conditions that life as we understand it would need. And the baseline for nearly every one of those assumptions is Earth. If Earth itself was cooling and recycling far faster than expected, hidden in plain sight for the entire history of modern geology, then the models we're applying to alien worlds light years away may be built on a foundation that needed correcting long before we ever pointed a telescope at another star. This is the uncomfortable, thrilling truth sitting underneath the surface of this whole story. We like to think of planetary science as something that happens out there, aimed at distant galaxies and exoplanets and the edges of the observable universe. But some of the most profound recalibrations in how we understand rocky worlds are happening right here. In rock samples pulled from ocean floors, in GPS stations bolted into Antarctic ice, in ancient fault lines running through East Africa. The universe's mysteries don't only live billions of light years away. Some of them are buried a few kilometers beneath your own feet, waiting for someone with the right instrument and the right question to notice them. So where does this leave us? Scientists still don't know exactly how many other hidden pockets of unusually fluid mantle exist around the planet, waiting to reveal themselves the way the Antarctic Peninsula did. They don't yet have a complete map of how many ancient dehydrated blocks of crust are quietly steering the shape of future continental breakups, the way that stretch of East Africa is doing right now. And they don't know with full certainty exactly how the accelerated cooling since Pangaea's breakup will play out over the next 100 million years. Whether the current arrangement of continents is approaching a similar breaking point sooner than the ancient supercontinent cycle would suggest. What they do know is this: the Earth beneath us has never been the frozen, finished object it appears to be from the surface. It has been rewriting itself in ways too slow for any human lifetime to witness directly. Until now, until our instruments finally became sharp enough to catch the planet mid-sentence, every one of these discoveries, the faster crustal recycling, the accelerated mantle, cooling, the astonishingly quick Antarctic rebound, the ancient chemical scars steering modern rifting, arrived only in the last decade or so. It's built on techniques and data precision that simply didn't exist when most of us were taught the basics of plate tectonics in school. That should tell you something important about the nature of scientific understanding itself. It's not a finished book sitting on a shelf. It's a living, evolving process. One where even something as seemingly settled as how fast the ground beneath us changes can be overturned by new,